Let's turn our attention back to uranium, far, far away from hydrogen. The uranium nucleus can have either 235 or 238 nucleons, and it's so large that the nuclear strong force can't reach across the nucleus. The outer nucleons feel the inner pull of the strong force almost like surface tension effects on water drops. And now we know enough to begin to understand fission. Suppose a very low energy neutron is absorbed by the 235 nucleus. It now has 236 nucleons, an even number, and therefore moves to a much lower energy state. This leftover energy can be thought of as causing the nucleus to vibrate or oscillate out of its spherical shape. If it oscillates into an elonged spheroid, the strong force, which already could not reach across the spherical nucleus, will tend to break it into two lobes, pinching off the middle and producing two new spherical nuclei sitting next to each other. We now have two highly positively charged nuclei sitting next to each other, and the strong force can't reach between them to overcome this Coulombic repulsion. They part ways violently, releasing 2 or 3 neutrons, a spray of electron, gamma rays, and neutrinos. First, let's look very carefully at these fission neutrons, because it is they who keep things going in the chain reaction. During fission, on average, 2.427 neutrons are released, with a kinetic energy of about 2 MeV each. If we look at the probability of these neutrons interacting with uranium to cause another fission, we see that the cross-section or probability is very low for high-energy neutrons and increases dramatically for low-energy neutrons. Well, how do we slow neutrons down? The answer is we let them scatter off things. This is a Faustian bargain because each time a neutron bangs into something, it could also be absorbed and lost out of the chain reaction. This is what we nuclear engineers do. We rig the game so that we can slow down but not lose very many neutrons. It turns out that the lower the Z of the moderating material that the neutrons scatter off, the quicker neutrons lose energy. Light hydrogen and deuterium are among the best moderating materials.